Hi, my name is Brian Caffo, and this is the lecture on power in the statistical inference class in the Coursera Data Science series. This class is co-taught with my collaborators Jeff Leake and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. So we're going to talk about power. So power, as its name suggests, is a good thing. So power, you want more power. Power is the probability of rejecting the null hypothesis when it's false. So there it is, in print. You want more power. A type 2 error, a bad thing, as its name would also suggest, an error, is failing to reject the null hypothesis when it's false. So the probability of a type 2 error rate is usually called beta, and then power is 1 minus beta. So let's talk about power. Power is an important concept in statistics. So consider our respiratory disturbance index example. We are testing H naught mu equal 30 versus HA mu greater than 30. So what's the power? The power is the probability. Remember, we were going to reject if our normalized test statistic, x bar minus 30 divided by its standard error, was bigger than a t critical value. But now, instead of just calculating this, if we were to calculate this probability under the null hypothesis, we would just get alpha, right? Because that would be the probability of rejecting under the null hypothesis, which we have stipulated to be alpha. But let's instead calculate it under the hypothesis that mu equals mu a for mu a some value bigger than 30. So remember, power, you got to plug in a mu a. You got to actually know a value of mu a. And then as mu a approaches 30, the power is going to approach alpha. Okay? So that's power. That's the probability calculation. Let's go through the math, and then we'll talk about it more heuristically after that. So 1 minus beta is the power. Let's calculate the power. So here's our test, and I'm ditching S for sigma just to make things less complicated. Okay, so instead of a T, we're going to reject with a Z. Okay, so we're going to reject if our normalized test statistic is bigger than the appropriate critical value, right? So here's the distribution of our normalized test statistic under the null hypothesis. We're going to reject if that normalized test statistic Z observed is bigger than the Z critical value, where that critical value is chosen so that alpha lies up there. Okay? But what we can do now, remember 30 is no longer the true mean. We can add and subtract the true mean right there. And then we get this guy, and we have subtracted this part from the other side. Right? So we haven't done anything. And so now this guy is a Z statistic, right? Before this guy wasn't a Z statistic. It was a Z statistic under the null hypothesis, but it's not a Z statistic under the alternative hypothesis, right? We're subtracting the wrong mean. Now, under the alternative, that's a Z statistic, right? So our probability is no longer our probability that we're calculating. If mu a were 30, this would be alpha, but it's no longer alpha, so it's the probability Z is bigger than this guy, right? So what does this guy depend on, right? So it's the Z critical value, but then it's shifted by how different your true mean is from the hypothesized mean under the null, but then that expressed in standard error units. Okay? So the idea is something like this. Under the null, here's our distribution of our normalized test statistic under the null. Here's our critical value, so that probability is alpha. Now, here's the distribution of the statistic under the alternative, right? Here's the distribution of that statistic under the alternative. And then here's that area. That area is power. Okay? So you can see how you can change power, right? You can move as this distribution moves around, it changes the power, and as this critical value moves around, that changes the power. So this distribution, the blue distribution, where it's centered at, depends on mu A, mu naught, and the standard error. So how do we use power? So what we usually, the way we do power, or the way we elect to use power, is prior to conducting a study, we choose our sample size so that we get a power that we want after we've conducted the study. Or, given a sample size for a study that we're going to conduct, we calculate the power a priori, just to make sure that the study is itself worth doing, right? That if the alternative is true, we have a reasonable chance of actually rejecting it. If the alternative is true, that we have a reasonable chance of rejecting in favor of it. So suppose we wanted to detect an increase in mean RDI of at least 2 events per hour above 30, given our RDI example. So assume normality and that the sample size and that the sample in question will have a standard deviation of 4. So what I mean is that sigma equals 4. Okay. What would be the power if we took a sample of size 16? Okay. So our Z statistic is 1.645 that we would want to, our rejection region is 1.645 or larger. We're saying this guy, mu A minus 30 over the standard error, right, is 2 because it's 2 divided by sigma we assumed was 4 conveniently. N was 16, so square root 16 we get 2. And so now we want the probability Z is bigger than 1.645 minus 2. And that works out to be 64%. Kind of a less confusing, a lot of these calculations we do these ways so that we can relate everything back to the standard normal. But another way to do this calculation would just be to do so our test statistic is x bar minus mu naught over sigma over square root n, and that's a normal 0, 1 under h naught. Okay? But what is it under HA? Well, it's still going to be normal, but we don't know what the mean and the variance is. But if we take its expected value, it's clear that the expected value is going to be mu A minus mu naught over sigma over square root n, and that its standard deviation, its variance is still going to be 1. Okay, so you could equivalently to doing these calculations, and I think you'll see that they would be the same. So we want the probability that this is bigger than 1.645 under this normal calculation, right? So we would want to do p norm, okay, 1.645, and then this quantity right here we calculated over here. It works out to be 2 under the hypothesis that the mean equals 2 and the standard deviation equals 1. And I think what you'll find, of course, that works out to be the same number. But remember that you need to have lower dot tail specified to be false, right? You want to make sure you get the right direction. Okay. So here, so just remember, this is the direction hypothesis. We're looking at mu greater than mu naught, and that mu is specified as mu A under HA, and that under H naught that statistic is normal 0, 1, and under HA, we just calculated it, it's that guy, and we're going to reject if Z is bigger than Z 1 minus alpha. And so what you can do is this plot right here, it can, let's see, there you go. It just shows the plot I've been drawing, but you can actually then go through it, and then you can actually change the value of this line, the critical region, right? So alpha is right here, and then the power is right there. And using this code, right, it's very simple code, you can move them around. And in fact, maybe some intrepid student can use the manipulate function and the and shade in the regions using a polygon. Okay. Where you so if you used manipulate, you could get it to where you turn the dial and change the rejection region and change the value of the alternative hypothesis and so on. So when you're testing, again, we're just still looking at this one directional hypothesis test to make things conceptually simple. Our power 1 minus beta is the probability of rejecting when calculated under the alternative, and we showed that it's equal to this, where it's a standard normal being bigger than Z minus that quantity, and that's the same thing as the probability Z being bigger than Z beta, right? And so this equation right here, Z alpha, so let me just draw a picture in case you're having trouble. So this is, let's say, the distribution, this is this distribution, which is a standard normal, right? The probability it's larger than this quantity right here, right? That is equal to, well, let's hope it's over here somewhere. That's equal to 1 minus beta, where this is beta right here, okay? And so we also know, yeah, that's beta right there. So, but we also know that the probability of Z statistic is greater than Z beta is 1 minus beta and beta right there. And we know what that number is, okay? So we can equate this guy in Z beta. So that guy is equal to Z beta. So here's my point. This is an equation now. And here's the things that we typically know is we typically know the value of mu under the null hypothesis, and we know alpha. But we don't typically know mu A, sigma n, or beta. But if you specify all of these except for one, then you can solve for the other one. So you can say, given my sample size, my alternative value, my sigma, what power will I have? Or you can say, given my, or what type 2 error rate, given my power and my n and my sigma, what's the smallest alternative mean that I can detect, right? So given any three of these, you can solve the remainder. That's the point I'm trying to make, using this equation. And then in principle, you can do that for any power calculation. So in other words, that there's always a set of things, if you specify enough of them, it yields the other one. Okay, so the calculation for mu less than mu naught is, of course, similar. For mu not equal to mu naught, then calculate the one-sided power using alpha over 2. And this is approximately right, but so close to the exact answer that it's not worth fussing about. Power goes up as alpha gets larger, of course. So as you require less evidence to reject, you're going to be more likely to reject. The power of a one-sided test is going to be greater than the power of the associated two-sided test, right? Because it's harder to reject for a two-sided test. Power goes up as the mu A gets further away from mu naught. Power goes up as n goes up, and power goes down as sigma goes up, which I didn't write, but also I would note, look back at our equation, right? We don't actually need that. It's a little unfair to say that we need n n mu a minus mu naught. We need n mu a and sigma, right? We need that ratio. So if we need the power, if we want to calculate the power only, we don't actually have to know these things individually. We just have to know this function, which is the difference in the means expressed in standard error units, right? So this guy, without the n, this guy right there is called the effect size. So it's often the case that we only discuss in terms of effect size. So that's this guy. And the reason for that is, notice this is a unit-free quantity, and it has some hope of being interpretable across settings. So for the t-test, we know kind of the equation we need to work with to talk about power. So we want the probability our test statistic is larger than a t, where under the idea that mu is equal to mu a, not equal to mu naught. Anyway, this statistic has a so-called non-central t-distribution, which is a little bit annoying to work with, and so we're not going to cover it, even though I think given the skills that everyone has in this class at this point, they should be able to. But it's a little bit technical, and I think if you understand the normal calculations, then you understand conceptually what you need to. And so what you can do is this function called power.t.test, which does it very well. And you don't have to work with the non-central t-distribution. And in this function, if you omit one of the arguments, then it just solves for it. It's a really nice little function. You can do 99, I don't know, that's an arbitrary statistic, but I find that almost all of my power calculations I can do with power.t.test. I think in general you want to simplify your power calculations as much as possible, because no one believes elaborate power calculations. Basically, if you do elaborate power calculations, people think you're trying to play funny games to do a experiment that shouldn't be done. So try and keep your power calculations simple. Here's here's kind of going back to our example. We're saying n is 16. Delta, which is the difference in the means, is 2, or is 1/2, and our standard deviation is 1. We want a one sample t-test, right? So instead of two group t-tests, we want a one sample t-test. We want a one-sided power, and we get 60%. I want to point out how this thing only depends on mu naught mu a minus mu naught over sigma, in that if I were to then take this 4 and move it over to the standard deviation, right, over here, then mu naught minus mu a, which in this case we said was 2/4, and in this case we said was 2/4, but specified with a 2 here and a 4 there, that we get the same answer, see, 60%. And then, it doesn't matter the scale, right? 100 and 200 is still 0.5 when you divide the two, and you still get 60%. So here's another way you can use power to calculate sample size. So here we specify the power that we want, 0.8. We give the delta that we want, and standard deviation equal to 1. So here's an example where we just specify delta in standard deviation units, and then we set the standard deviation to be 1. Okay, and then we grab n, and we get that it's 26. You always round it up and just say 27 then. Okay, and then again you can see that you get the same answer. You get 27 if you do 2 and 4, or 100 and 200. Okay, and so that's a survey of a very brief survey of power. Power calculations can be tricky. There's a lot of dials, and you can fool other people, which you shouldn't do. But you can fool other people because there's enough things that you can change, that you can get your power to say just about almost anything, if you twist the dials enough. So it's important to do, and more importantly, even though I think everyone who's honest isn't going to try and fool other people, but the important thing about power also is it's easy to fool yourself. So think carefully about your effect sizes, think carefully about that you got all the settings kind of the way that you want them when you do power, and kind of check over things very carefully, because they're very, very easy to mess up. Even though they're simple, but they're simple in a way that makes them kind of error prone. So be careful with your power calculations. But hope and the one thing I would say is be careful, and then the one way to execute being careful is always to try and make your power calculations as simple and as kind of robust and conservative as possible.